clear the other data. Let's see what happens when we transform this with logs. So I'm not going to call it child transformation. I'm going to call it child TR, because for some reason it gets saved in my calculator, and I don't know if I'm going to end up using the T or the old one or the new one, so I'm going to call it TR. I'm going to just work with the natural log, but you can also do this with the regular base 10 log. And I'm going to call it income TR so that when we're comparing it, we can tell. I'm going to go to a scatter plot for these. So remember, the whole point of this was because we can't really predict what's going to happen when we have the curve plot like this. We want to have a least squares regression line. So let's try to transform one of the data right off the bat. It looks much more linear. So just taking the log of the income, the natural log of the income. This is with the natural log of both, the income and the child. That looks even more straight of a line. This is just a natural log of the child mortality rate. That's probably the weakest, I think, version of all of them. So when we're going to compare them, we want to have some actual least square regression line so that we can do some predictions here. That one I think is probably the best one out of all of them. So the least squares regression line for this one is this 11.4948 plus, and it has a negative in there too. I don't know if you can tell. We'll jot this down in a second. Where just the child is transformed, and this one is where they're both. That's back again. And this is where just the income is transformed. We have 3 different transformations that we could end up with for this one. Now, if we want to skip ahead and look right at the residual plots, this is what the income and the transformed income only residual plot looks like. It doesn't look very scattered. Now keep in mind when you go to do the other one, this one is transformed for both. That's a perfect residual plot. It looks scattered, doesn't have any type of pattern, a little above, a little below. Absolutely perfect fit right there for it. Now when I go to do the child transformed, the reciprocal or the log of the child, I have to redo the residual plot. Sometimes my calculator makes me do this. Just doesn't look as good. You can see the difference between the two. That one looks a heck of a lot better. So if you would, let's not focus on any other one because we know those ones don't fit as well. So let's go to transformation, the one where we took the log of both. Let's not do a transformation 2 or 3. Those really just don't fit that well. This one is the one where it was the natural log of the income equals 11.4948. There's a plus, a negative. I'm just going to copy exactly what it said on the screen. But hopefully you know that when you plus a negative, it's actually the same thing as just subtraction. And it's the natural log of both the child and the income to be able to do that. So let's try calculating this. And again, I'm going to cross off the transformation, that one and that transformation, because it really is just not applicable when you looked at those other plots, especially those other residual plots. More scattered, more accurate. So transformation number 1, I'm trying to predict the income. So that's my variable still. But I have all this information. I'm going to change this to a minus because I just don't ever keep plus or minus like that. Times the natural log of 20.3. So when I do the natural log of 20.3, times it by 0.93737 and subtract that from 11.49. This is where you need a little bit of your algebra skills to come back to you. I'm getting 8.67273, something like that. So hopefully you're remembering that this is the natural log of the income. So that's not the income. You have to get it out of this form. And keep in mind that the base on this one is like a little e. And you do base, logs are exponents, so we put that as our exponent, will equal the income. And our calculators will calculate e to the 8.672373 power. And I'm getting around 5,841.45 as the income. Now let's compare this. The last one that we did was 63. We felt that was one of the best ones. So let's look at the R squared for this. If I do the stat calculations, now this was just the transformed value of the income. So you can tell it's 0.87, negative 0.87. When you square that, that's going to end up being something like, I did that, 76%. So that's not that strong. This is an example of doing the child transformed and comparing it to the income plane. R is 0.83. So 0.83 squared is actually worse. That's 68 or 69% accurate if we're doing percentages wise for the variability explanation for. So this is when we transformed both of them. Transform the child, transform the income. It's the natural log of both, and we end up with an R of negative 0.96. And when we square that, that's where we end up with, we'll go back to our sheet, R equals, and again, we don't have to write down those other ones, but I did want you to see how the differences are in the R value. So for this one, we end up with R equals negative 0.962 or something like that. So our squared value was 92.5. And it's pretty tied with the last one that we did on the front part of this page that was also around 92%. But the residual plot is really much more accurate. When you look at transformation number 3, I don't know if you sketched it, but the residual plot was just so much more scattered. No pattern, but really filled in and used the whole entire graph as well. So to me, I think this is the best possible way of predicting. Notice the prediction was about 5,800, a little off from the past one. So both of these ways give you a good outline as to how to predict, even though you have curved data or nonlinear data. So you want to go through different ways to transform to be able to get linear data, to come up with a regression line, and be able to predict one of these outcomes.